morning. It's from a Feynman lecture, and Feynman's lectures were quite incredible. If any of you have listened to 6 Easy Pieces or any of them, I'll read this one, and it's a poet, I think, once said, "The whole universe is in a glass of wine." We will never know what sense that she said that, for poets do not write to be understood. It sounds like a slam on girls, I think, but that's what Feynman, it was about his poetry. But it is true that if you look at a glass of wine closely, you will see the entire universe. There are many things of physics, the twisting liquid, the reflections of the glass, and our imagination adds the atoms. The glass, a distillation of the Earth's rocks. In its composition, we see the universe's age and the evolution of the stars. What strange array of chemicals are in the wine? How did they come to be? Where are the ferments, the enzymes, the substrates, and the products? There in wine is a great generalization. All life is in fermentation. How vivid is the Clarnay, pressing its existence into consciousness as we watch it. In our minds, for some convenience, we divide this glass of wine into this universe. The physics, geology, astronomy, psychology, and theology. Remember that nature doesn't know the difference. Nature doesn't put divisions on these things. So as we put it all back together, let's not forget what it's for. Let's give one final pleasure and drink up and forget about it all. Well, as Earth Day, we don't believe in the supernatural. Earth Day, that as a humanist, we don't believe in the supernatural. However, the laws and principles of quantum physics and relativity are almost kind of like the supernatural. Does that mean we don't believe in the universe? I don't know, But maybe we need to amend the Humanist Manifesto number 3. But we'll see about that. Now, last week we had a speaker Michael, and he said that it was about human psychology, and if we had death on our minds, we didn't believe in the afterlife. But I think if we were a soldier in Iraq or Peru fighting for our oil or our copper being shot at by a sniper, I would think that the soldier would want to believe in the afterlife. But in the strangeness of the universe, with a quilted multiverse and quantum entanglement, the universe is beyond supernatural. It doesn't matter what we believe, that nature will do what it does. Nature does not care about climate change. Nature does not care about nuclear holocaust, but it is our job to keep nature in balance.
Thank you. Our programs are based on 4 broad areas relevant to humanism: human well-being, science reason, secularism, and humanities, culture, and morality. This morning's program is part of the science and reason section. Joyce Lackey, would you please introduce our speaker?
Duane Ray, physicist and former member of HGP, has spoken to this group on topics from quantum mechanics and relativity to the nuclear power issue. With degrees from Swarthmore College and the University of Pennsylvania, Dr. Ray is retired from a career with AT&T at Bell Laboratories. That retirement has allowed him to pursue his interests in protecting the Columbia Gorge, the concrete house he built several years ago, and photography. Duane was able to satisfy an interest in both science and photography last year by claiming a campsite very near the path of maximum totality of the solar eclipse. In his words, great campsite, camaraderie with everyone, kids everywhere. The only drawback may have been that the pleasant 2-hour drive to Madras was followed by an 8.5-hour return trip after the eclipse. Traffic was moving along so well that his son got out of the car and walked part of the way. But for the opportunity to see his first and last total eclipse, the inconvenience was worth it. Modern science describes our universe from the original Big Bang to the present and the many solar systems we have now discovered. There are holes in our understanding, however. Dr. Ray provides an overview of current knowledge and offers suggestions about what the future may bring. Please welcome him.
Any time I have a chance to talk about science, I'm there because I think it's really so important. Just a quick political thing. When Betsy DeVos, Secretary of Education, does not believe in evolution, Secretary of Energy, in one of the presidential debates, he was one of 6 that raised their hands when they were asked about who believes in the 6,000-year-old Earth. This guy is trying to get rid of any kind of restrictions on people. And the Obama White House had 100 people in the science and technology group contributing ideas to him. Trump has cut that to 50, and I don't know where it might be now. Let's all open our science books to chapter 1, verse 1. That's the creation view. And to remind you, the constitutional ban on teaching creationism in public schools was narrowly upheld at the Supreme Court of the United States in 1987. And you may remember that there was a Dover, Pennsylvania court case where they tried to sneak in intelligent design and call that science, but that was also struck down. So they're among us. They're just trying to do it. And in addition to that, there are people like Ron Paul, who said he's reading on page 207 of the 2,000 plus pages to go. Paul tweeted at one point, reading about the ever-wasteful $6 billion National Science Foundation. They're the ones that put all the fundamental money into a lot of fundamental stuff that nobody else has a reason to support. Drug companies and all that kind of stuff do it with a make money thing in mind. They do it because they want to get some basic science supported. Last year it was $7.5 billion. Now it's down to $6 billion. So things are not on the right trend for people in the United States. Okay, but we're really here to talk about science and the universe and so on, so let me talk to you a little bit about that. Back in 1610, we started getting a broader view, looking through a telescope and finding out more about the universe, and it really kind of blew us away. Since Galileo discovered the universe in 1610, things have become a little more complicated. If you read anything, you're probably well aware of that. E equals mc squared, gravitational wave, quantum mechanics, black holes, you name it, we can come up with it. Neutron stars, dark matter, multiple universes, and it's all very important to lay the groundwork for our understanding in the future. Just think what's happened just 100 years ago. We didn't know about this stuff. X-rays, radioactivity, radio communication, energy is quantized. Atom is quantized. General relativity, I mean, that's really something special. And then quantum mechanics, everything is probabilities. You got to be kidding. Transistors, lasers, all that kind of good stuff is based upon a good understanding of what those things are. A lot has happened since this 100 years ago. So we need to be aware of what's happening and where we're going. Let me talk a little bit about technology because that's part of the train that's moving our science capabilities forward. Back whenever I first joined Bell Labs, back in the late 60s, I had been hired because of my magnetic background, and the question they were trying to decide at the time was, will silicon memory ever get down to less than 1/10 of a cent per bit? Because that was the going rate. You wanted memory, 1/10 of a cent per bit. And anybody that worked in those things and had a new computer realized that if you had a computer with 32,000 bits of information, man, that was a pretty strong computer. Well, here's a 64-bit magnetic memory compared to an 8 billion bit memory. Quite a difference. This is a 128 gigabit, cost $18.99. You just walk and take it off the shelf. 128 billion bit memory at 1/10 of a cent per bit would be $128 million. So we've come a long way since then. Great benefit to have that. Okay, we know a lot, still a lot to learn. Where did it all come from? What's out there in the existence we're still unaware of? There have been surprises recently, perhaps some more surprises in the future. Okay, let me talk a little bit about the Big Bang, because that sort of is the basic. We're trying to go back and understand a lot of things happen along the way, and it kind of crosses all the things from chemistry and quantum mechanics and physics and relativity and all those different kinds of things. Back in the beginning, there was nothing, not even space. And all of a sudden, something happened. We have no idea what. Something happened, and within about the first 10 to the minus 30th of a second, it grew from nothing 50 times faster than the speed of light to about the size of a basketball or maybe this room. Faster than the speed of light? Nothing can go faster than the speed of light in space. This was into nothing, not space, not empty space, nothing. So now we have this, and already there's some slight undulations in the density of the sphere that's expanding. So it continues to expand, and after about 380,000 years or so, this has been so hot at the beginning, and the only thing that existed there were neutrons, protons, and electrons. And the protons and electrons could, of course, form a hydrogen atom later whenever things weren't so hot. They are all ionized now. Neutrons by themselves are radioactive. They decay with a lifetime of about 10 minutes into a proton and electron, so they separate out. And it's still so hot that the electrons cannot form a hydrogen atom by staying associated. There's just too much energy. After about 380,000 years, it finally cools off enough now, and beyond that, the electrons are able to settle onto this proton and become a hydrogen atom. And once that happens, the electrons don't interfere with photons anymore, so all of a sudden the universe becomes transparent. So a photon can go from here all the way over there, maybe not bouncing off anything, just going past these neutral hydrogen atoms, okay? And then it continues to expand, and after about 180 million years or so, some of the, remember those undulations of a little more dense here, a little more dense over there, and not quite so dense in here, so some of the matter up here is attracted a little more to the matter down here than it is to the matter up here. So it starts falling gravitationally toward this, and it gets faster and faster, picks up gravitational energy, and of course the stuff down here is being attracted up this way, and it's moving faster. Pretty soon they get in there smashing into each other and transferring this energy of gravitational into heat energy. They're bouncing off each other, and this stuff keeps coming down. And it's a huge thing that finally there's enough hot material in the center part of this that it gets hot enough that it can start having fusion. So these hydrogen gets converted into helium, and you start getting more energy out. So that starts making these things hotter and faster, but there's still pressure of things outside coming in, and finally you have a star is born, okay? So now you have the hydrogen being converted into helium, and the helium gets converted upward into carbon and nitrogen and some of those other things. And every time you make this transfer of the nuclei into higher nuclei, you get energy out of the system until you get up to iron. Above iron, you have to put energy back in. So we don't get a lot out of that. But these initial stars are very big because it's just hydrogen and helium. Then they blow up, and in about 300 million years or so, give or take, now you start other stars being formed from the material from the stars that initially were there that blow up. But now you've got some of the higher elements. You've got iron, you've got nitrogen, you've got oxygen. So in addition to the stuff that's going in the middle, you have some debris around, and those turn into planets. Okay, so now after about 380, 400 million years or so, you have some stars around with some planets. And then we move along from there, and I'll carry that through here. And that's sort of what this has to do, but let's go back and look at this. This is much later, and not only do you have stars, you have collections of stars, and angular momentum is there, and so you have these beautiful swirls of galaxies that form, and on and on and on. One of the guys who was instrumental in deciding or determining and creating the formulas that talked about the Big Bang initially was Mr. Inflation, Alan Guth. He was MIT at the time, I think, and a graduate student. He went on to be a professor there. And also apparently a very messy guy, because one of the newspapers in the Boston area had a contest for who had the messiest office in the region, and he won. Mine doesn't look quite as bad as that, but I'm not in any contest either. One of the other things also, and by the way, I had these handouts that many of you have now. I don't know, I brought a bunch. And that also is for a talk that's twice as long as this, so it has some material in it that you won't hear today, but it does have a lot of this kind of stuff in it, and the references to go back and look if you really want to chase some of that stuff. The Big Bang is one possibility where it all starts from some tiny thing, but there's also other possibilities that quantum mechanics and so on allows us to have. And that is if we have the cyclic model, where you have a universe here and a universe here, and they're drawn toward each other, and they get closer and closer until finally they hit each other and kaboom, and maybe that's what the Big Bang was, and as things go forward in the future, it starts all over again. So maybe there's a cyclic kind of thing. We haven't come across science that rules that out yet, okay? You can find some references there. Once you start talking about other universes and nothing in between, not empty space, nothing, then you talk about some possibilities like this. Are there other universes out there that we can't make contact with? Who knows? Maybe they look like this. Is our universe one of these condensations? I don't know. Maybe we'll find out, maybe not. Maybe the Big Bangs are where these little things sprout off from previous universes. We don't know. That's still to be determined. Maybe there's totally different types. Maybe iron and oxygen and protons and electrons don't exist in these other things. It's some other kind of Dizwammy 1 and fertile number 2 and who knows what, but different kinds of styles. We don't know what's out there. We don't really understand enough to be able to make any definitive statements in that direction. One of the things that's really impressive is that we look at our universe and there's an awful lot of information out there, a lot of really neat stuff, and it's by observing that we're able to come to the conclusions of things that we know about today. This is a Hubble telescope. Whenever back in the early 90s, whenever December 95, the guy that was taking over the Hubble telescope project at the time said what we ought to do is we ought to take a look in some deep, really far, far away, and what we'll do is we'll take the Hubble telescope, which is above the Earth's atmosphere, and we'll point it in some direction where there's nothing there that we can see from here, from the Earth, and we'll take a really long exposure, which was about 3 days of exposure over a period in December, and what they found was this. Every one of these is a galaxy. And if you want to look a little closer, the patch of the sky was the same size as a tennis ball placed at the other end of a football field. So it's a really tiny part of the sky, but we see all this stuff in it. Okay, and if you look really close, everything here is a galaxy except maybe something like this. So the more you look, the more you see. We're just loaded with galaxies, just incredible amount of information. But on the other hand, that gives us a scientific laboratory that we can go in and by observing a wide range of things that is there, which means not only the type of thing, but also the time at which they were made. So there's a time element to it. We can really examine that and try to understand more about the universe that we live in. These are some of the examples that they started with. Back in 1992, they started this, which goes up and looks at the background temperature measurements. Remember I mentioned that whenever these things, these stars are coming together, well, there's still some debris of hydrogen and things like that laying around in the atmosphere or in the universe that doesn't get clumped into these stars. There's an awful lot of material out there that never gets clumped down. So that's a background. The temperature of that is just slowly cooling off as this universe is expanding. Well, we're looking at the temperature of those background molecules that are just floating around between the galaxies. Ignore the hot stars and the hot gas clouds that are lit up and so on, but all this gas in between the whole universe, that's what we're looking at with this. And then in 2009, we got a little bit more advanced technology, so we're able to make a little bit better measurements of that. And then finally in 2013, we came up with this. And of course, these are the different satellites that are up there above the atmosphere that are making these measurements. And if you take an overall look at the whole universe around, you put that on a flat piece of paper and it can look like this. And the accuracy is 2/millionths of a degree Kelvin by the time you get to 2013. So we have very accurate measurements, give a lot of very interesting information about what's out there, and all of our theories, of course, have to fit that in order to be able to go forward. This is just a bigger piece of it, and it turns out that the size variation of these little dimples that you see in there, we do the calculations and stuff, you really have to have dark matter. And that gives yet another confirmation of dark matter and how much is there. One of the other things that's very interesting, let me lay the groundwork for this, in order to be able to get really good information about what's out there, you have to know how far away it is. You don't know how bright it is unless you know how much intrinsic brightness is, unless you know how far away it is. So if you have some standard bulb here, like a 50-watt bulb or something, and you take it pretty far away and you measure the brightness out there, and you know the brightness intrinsically here, you can really calculate how far away the guy took the bulb by measuring its brightness, because you know its intrinsic brightness, and you know the brightness here, and 1 over r squared, and you go through the calculations, and you can calculate within very good accuracy how far away that guy has taken the light bulb. Well, what we need is something like that in the universe, and we have it. We have a supernova. So in this big thing, down here there was nothing. All of a sudden there's a big splash of light. This happened back in 1987. A guy down in Australia was doing some telescope work at night, and he took a break and walked outside and was looking at the sky, which is fun to do in a dark sky. And he said, gee, there's a spot of light up there that shouldn't be there. Wasn't there before. So he called a whole bunch of the people around, and everybody started, all the astronomers started looking at this and started making measurements. And that was the first really significant supernova, and I think that was back in 1918. One of the other things that was interesting when you go back, everybody's making their measurements, doing their thing, and they don't always know that they're related to one another, but people were measuring neutrino interactions, and that's really tough to do. You need a huge thing, bigger than this room, and maybe once in a while you'll get a neutrino hit, because there's 1 billion neutrinos going through my thumbnail every second, but they don't interact very much. They're from the center of the sun, and they get to the surface of the sun much faster than light does. Neutrinos just come out. Light takes maybe, I've heard different numbers, 400 years or something to work its way to the surface of the sun. Neutrinos come out instantly. So they go back and they look at neutrinos that were from this Big Bang, and they find some other stuff. Total of 25 neutrinos. Just another little bit of science to add to make sure everything is consistent and perhaps give us some new directions to go in all of this. Okay, well, I talked to you about how we want to use this as a standard light bulb that we can carry out to different distances. So if we can recognize these supernovae, and if they're the same supernova, then we're in great shape. We have a standard bulb that we can use to measure actual distances. Well, as a star goes through its lifetime, it's a star, then as it burns out most of this hydrogen, helium, and it grows to the higher things, it ends up turning into a red giant, which gets dimmer and so on and reddish. And then it runs out of fuel. So all of a sudden, it doesn't have this radiation pressure pushing out against it, and everything comes down and collapses, kaboom, and you end up with a remnant, which is a white dwarf, which is a white dwarf, okay? It's sitting here, yeah, a white dwarf. It's written there, I can't read my own stuff. Now, one of the things you also should know is that if you look up in the sky, about half of the stars are really double stars. So if this happens to be beside a companion star, here's this white dwarf, and it keeps accumulating various gases that are being blown off by this companion star, just like our sun blows off stuff all the time. So over a period of years, you have this little bit. It's like adding a little bit to the scale until finally it goes clunk. It's reached a certain point. And for every scale where you're adding this little bit, it goes clunk at the same time, because these are all standard-sized things. And boom, you have a supernova. So now we found something that's standard brightness, and if we can recognize those throughout the sky, we see the brightness, we know how bright that is, we measure it, we know what its absolute brightness is, and we can measure how far it is to that. Okay, another thing that we want to do, by the way, yeah, sometimes two stars collapse and form two neutron stars. We'll talk a little bit more about that a little bit later. Okay, here's another one, and notice this was found by an automated review of images in the pinwheel. There's just so much stuff being collected out there that it's nice to automate some of these things to pull out the information that you're interested in. So that's happening also. So here is this star that blew up from down here. Okay, if things are expanding like this, and we know our universe is expanding, one thing I want you to notice is that we're here, and as I move here, a uniform expansion, if it's twice as far away, it's moved twice as far from me in that same amount of time. If it's 5 times or 6 times as far away, in that same amount of time, it's moved just the same amount between these two, but from me over here, I add up 1, 2, 3, 4, 5, 6. It's moved 6 times as far, so it's moving away in the same amount of time 6 times as fast. So I can measure how far away it is by its brightness, and I can measure how fast away it is, how fast it's moving away from me by the Doppler shift. So we have a combination of things now, and we can find out how fast our universe is expanding. And we have the tools to do that. The dimmer they are, the faster they move away from us is what we find uniformly. What we end up with after putting all this stuff in the equations and so on is that our matter is just about 4 or 5%. Exotic dark matter is 26%. Dark energy is 70%. The most recent things, Wikipedia 2018. Wikipedia is a good go-to for this kind of stuff. So we're about 4.9% of the stuff in the universe. Pretty insignificant in the scheme of things. Exotic dark matter and dark energy, we have no idea. We have no idea. But we can do some things that depend upon that, so we can start whittling around and getting some ideas about what this dark matter is, getting some characteristics of it, how it's distributed throughout the universe. And that's what this simulation is done. So if you start off with initial conditions that are sort of what we expect to be, and then let gravity take its toll, and you run the simulation, and you end up getting things like this. And gee, you know, that looks pretty much how things are distributed throughout the universe. So this model is getting pretty close. We can really start to believe it. And dark matter is required to properly explain what we see. So that's another indication that we really are starting to require dark matter in there and to learn about it. One of the other things that's interesting is we can find out how fast some of these things are moving, because I should have this white. Can you read that? Dark matter, if it's moving fast, and dark matter if it's moving slow. And this is what it looks like. So this is slow-moving dark matter and everything. A bigger, more complete demonstration shows the same thing, just in a little bit more detail. So let me tell you what we've learned about dark matter. This is dark matter in 1933, and this is dark matter in 2018. So I'm afraid we're just there, folks, and maybe sometime in some near future we'll find out. There's only one experiment that has, in fact, said that they have detected dark matter, and everybody sort of says, yeah, right, but. And they are the only person out of many experiments around the world who are trying to find dark matter, and the other killer is that they won't let anybody see their data. So they're real legitimate scientists and stuff, and they've been saying this for a long time, but people try to repeat their experiment, and nobody's able to do it. Now, they happen to be under a huge granite mountain over in Italy, so maybe that has some, who knows, they don't understand it, but they're insistent that they're really doing it. Let me talk to you a little bit about gravitational wave detector, because that's going to be important in a minute here about things. This is out in LIGO. This is out in Hanford, near Tri-Cities. It's not really too far from here in Washington State. And this is about 4 kilometers long, 2.5 miles. Another one 2.5 miles out here. Initially received $300 million from the National Science Foundation, that they're trying to downsize the amount of money is being given to them. Here's LIGO. Again, this is out in Hanford. These are all pictures I took out in Hanford whenever I visited there. I've been there a couple times. It's really kind of interesting. Back in the early days, they actually used to let you walk into the laboratory and see this stuff. Now it's a little more restricted. I think you can see it on certain days of the week, but call ahead if you really want to go inside and see things. Inside that concrete is a 4-foot diameter metal pipe, stainless steel pipe, which is totally evacuated, and that's what our laser beams go down and back for. This is a suspended mirror. The most recent one is 40 kilograms, and the idea is to keep the isolation from out there. And whenever I was visiting the first time, they were telling us about these things, and they say, see that guy over there, his name is Schultz. He's our standard Schultz. Yeah, Bob remembers. I think he was on that trip, actually. And what do you mean, standard Schultz? Well, we asked him to go out 100 yards into the desert and jump. Okay, we saw that. He'd go out another 100 yards. Yeah, we saw that too. So they could kind of hone their skills in detecting these minor variations. And they said there's one thing, though, that we couldn't figure out. We saw this standard little glitch. And it wasn't at a standard time of day or anything, but it was the same shape, okay, and this vibration. And we couldn't understand what it was. And then finally one of the guys said, I'm going to call the airport. So I called the airport, and sure enough, whenever there was an airplane taking off and going over the top of them to some other location, that's what caused it. And when you think of, airplanes, to stay up in the air, they have to push down on the air, okay, and that was enough to change the distance. That was when they were just getting started, okay? That's the kind of sensitivity they had to have. And of course, they had to have isolation really big in order to keep the trucks rolling by from impacting things and other stuff like that, earthquakes, tides, and things like that. Okay, so each mirror, this is probably more than you want to know about it, 40-kilogram mirrors, cylinders. I mean, they just hang it to isolate it as much as possible from vibrations that are caused by the ground. These are pictures of the first gravitational wave from big black holes that merge with one another. And this is, the idea is that you have to, I forgot to mention, that you really have to have two places. We have one here in Hanford. There's another one down in Livingston, Louisiana. And the thing is, if one guy says, I see it, and nobody else says it, well, you wonder if you just have a problem with your equipment. But if two people see it, then you say, yeah, that's a real event. And not only that, the fact that Livingston saw this 7 milliseconds before Hanford saw it, you can sort of get an idea of what direction it's coming from, because gravitational waves that move at the speed of light. So these are the things that allow them to say, yeah, we saw these two big black holes. They could get the size of the black holes and their merger. And they saw this, 7 milliseconds, so they know the general part of the sky, but that's about it. And I want you to take a look at these particular things. This is 10 to the minus 21. And you notice you see a lot better resolution really than the 10 to the 21 would indicate. Well, here's a typical galaxy, 180,000 light years across. Our galaxy is maybe 100 to 180,000. Andromeda is maybe 220,000. So this is not an unusual kind of galaxy. If you measure the distance across that galaxy with the same kind of accuracy that they measure the distance between these mirrors, you're measuring it to less than 5 feet, okay? So we're really doing pretty good, folks. And they've shut down now so that they can upgrade that, and I don't know what they're going to upgrade it to, but they're going to get it even better than that. So it's absolutely incredible what people are being able to do these days. Okay, let me go back and review with a timeline of the universe. If this is the beginning of the universe, and this is sort of what's in the handout that you have with some notes and so on about everything. Billions of years, and we know that we're here at about 13.8 billion years. And here's where we're going to walk through this. The universe begins, and it keeps going, at least for a while. First stars form here very early. Remember, those were all just hydrogen and helium, and none of the heavier elements were there. So they had to blow up, spread all of that stuff into the universe around it, and then you had more stars form with those, now including heavy elements, and also with planets around them, perhaps. And the first planets are being formed by the time you get this stuff. And after you have some planets, you can have some first life. Now notice this is way back pretty much in the beginning, just roughly. And since we know about how long it takes from first life to get to intelligent life like us, it takes a little while. Life on Earth, our sun didn't start until pretty well along with things. Okay, about 4.54 billion years to us. And we know that eventually, from the kind of star that we have, it's going to blow up by the time we get over to here. Possible intelligent life was maybe 9 billion years ago, which has to do with the UFO stuff in the handouts and stuff, but that's another whole story I don't have time for today. Too hot for life? Well, yeah. Here we are now. Here's the proposed what's going to happen to our sun, and we are right here. By the time it starts getting pretty warm up here, we're toast, or we're going to have to find another planet or someplace to go. Small stars with planets, they can last for hundreds of billions of years, small stars. So that means if you have a planet around a small star, life could go on there for a long time. And remember, that could have started way back here, billions of years before we got here. So are we alone in the universe with all those stars and galaxies and stuff? Not likely. Why aren't they here? Good question. That's part of my UFO talk. We'll get to that some other time. Other worlds with other life? Well, maybe. The Big Bang this goes back to 10 to the minus 43 seconds. Right after our theories of quantum mechanics and relativity work back to that period of time. Before that, things fall apart and we really don't understand it. But from that 10 to the minus 43, everything kind of fits together. That's what Guth said and what he went. So we're really pretty damn good. We don't have all the answers, but we're no slouches. Guth showed the universe expanded exponentially during this period of time to 3 times 10 to the 17 meters. At our current time, the size has grown to 3 times 10 to the 42 meters, far exceeding the visible universe. So there's stuff out there we'll never be able to see because it's so far and moving so fast. The light won't have time. Anyhow, we won't be aware of it. Universe, 10 to the 26 meters. Okay, first stars formed 180 million years after the Big Bang. You had fusion light elements to iron. Then you had also neutron stars. And we know about neutron stars, and maybe neutron star mergers formed some of these lightest elements. Perhaps limit the causes of expansion, are the causes of previously examined gamma ray bursts. We've recently observed with LIGO the merger of neutron stars, and that does 2 things. One is it explains how some of the higher elements are produced in the periodic table, and some of the news things said, yeah, whenever those neutron stars merged, they made 10 Earth-sized clumps of gold. Gold always catches everybody's attention, okay? So they made as much gold as would be the size of 10 planet Earth things, okay? Also, there was a burst of high-energy X-ray kind of things, gamma rays, that had been totally unexplained before, but now you get a burst from those every time you have a neutron star merger. So these few bursts that we have seen, and I remember back in the day, people were wondering, are the Russians testing nuclear bombs out in space to keep it away from us? Maybe that's one of the, and that was finally eliminated as a possible cause. So we're starting to learn a few more things about what's going on. Large black holes form from dark matter. Well, they don't really know. Probably not, but maybe. Small black holes evaporate to give some of these fast radio bursts. Alternative universe is a possibility. We're still very much in the unknown in a lot of these different areas. One of the things, the experiment that's going to be putting up is LISA. It's a laser interference space interferometer space antenna, and it's going to be put up out beyond the Earth-Moon distance, and it's going to be a few years, I think probably in the early 20s it will go up. 5 million kilometers between these, so it'll be able to measure a different realm of these space gravitational waves coming across. Your LISA Pathfinder demonstrated that we have the needed capability by sticking this thing up and making some measurements with it in space. And we find that, yeah, if we put this up, we will be able to make those measurements and they will work. So it's going to be like this. It's going to be following, I think it's going to be trailing Earth around the sun and in orbit with us, but out beyond our moon. Let me talk a little bit also about now planets around suns. And right now, we have our sun, we have several other planets. This is distorted a little bit. Venus should be just inside this zone of life. And this is where we are kind of in the middle. We're moving as time goes a little bit away from the center of that. But this is where you have a zone where the sun is not too hot, not too cold. By the time you get out to Jupiter, Jupiter is just a planet of gases. It was so cold that all those gases just clumped into a big Jupiter-filled gas thing. But it would be too cold for us as humans to live there. But in this range, it's a possibility. Mars would be a possibility. It's on the outside. But for the future, as our sun gets expanding and hotter, Mars would be another possibility. Okay, if we have a smaller sun, then the habitability zone is in much closer to that star. So we would be out beyond that, but it has a lifetime of, say, 50 billion years. If, however, you have a much brighter sun. You have a huge habitability zone out beyond where Mars is in this particular scale. But the lifetime is only about 4 billion years, so life would have a chance to maybe get started, and then poof, you're gone. So I guess I'd rather be with a small star than a big star, but that's the way things are happening. So if we're looking for life around a star, we know what kind of stars to look for. Here's our particular situation. Here's our sun. 3.5 billion years ago, the habitable zone was out here, and here is our Earth, I believe. Here we are today. We're kind of on the inside of it. These aren't scaled exactly properly. You kind of push them together and get into ballpark. And another couple of billion years, we'll be inside, will be too hot, so either you have to turn your air conditioning up really high or you're dead. So it's that kind of ballpark we're talking about. The other advantage we have is that we're in a place in our galaxy that's also fairly stable and okay for life to exist for a long period of time. This is our surroundings with some other stars and so on. And National Geographic put out a list of things that made life on Earth possible. Our planet recycles life-friendly over time. We have an ozone layer to block harmful rays. Big moon to stabilize our axial wobble. Earth's varied surfaces support many life forms. Our magnetic field deflects solar tempests. We're just at the right distance from the sun. We're situated safely away from gas giants that might blow up and create problems for us. The sun is a stable, long-lasting star, relatively speaking. We have the right stuff to host a dynamic core. We have giant planets that protect us from afar. Remember there was a gizmo from outer space that came in and broke up into several pieces and fell into the side of Jupiter, and there were, I think, between 20 and 30 pieces that they noticed went in, and the size of hole or mark that they made in the gas surface of Jupiter was bigger than Earth. So if any one of those would have hit us, we'd have been toast. Our sun protects us from galactic debris. Our galactic path steers us clear of hazards. Our location is far from the stellar crowd, so you don't have other things that are going to be happening to you. Yeah?
The number 1 on there, I don't get that. What is that? Number 1, what does that mean?
Our planet recycles life-friendly over time.
What does that mean?
Well, I think that it probably means that we go through evolutionary kinds of things. You know, we have different amounts of CO2. I mean, all of this stuff recycles. The CO2 gets turned into carbon, into coal, and we bring that back out again, and the plants recycle it back into hard stuff and gets it out. We've had as much as, I don't want to give numbers, but very high numbers in terms of oxygen at some point, CO2 at other points. So it cycles through all of those, and we happen to be in a sweet spot right now, but all this stuff that we're burning to get energy to put CO2 back in is changing that sweet spot a little bit. Maybe within our lifetimes yet. Okay, the evolution of a solar system, just quickly, it's kind of obvious here. You have a sun, and this debris is swirling around. You have a certain amount of angular momentum, which is why things are pretty much in a plane, and you end up with a system that looks like this. This is Orion. Yeah, the question is, how unusual is this? Well, if we take a look at Orion, which is a pretty obvious thing in the sky that many people see with that belt of Orion and the sword down at the side, and you look more closely here, you have a nebula in there, and all of these gases swirling around various stars and so on. And if you look at that more closely with a good telescope, you can find innumerable places where this gas is clumping so that you would end up with planetary systems being there. Are we getting close to question time or something? Or, oh, okay, we still have a little bit of time. This is one of the telescopes that was put up in orbit to make measurements of the brightness of other stars. And what they do is measure a star, find out how bright that star is, and then measure a whole bunch of different stars, and then come back and measure that star again, and go and keep cycling through this. And they end up getting a whole bunch of points, and if they see the brightness dip like this, it's because a planet has gone around and moved in front of that sun and made it brighter for that period of time. So it measures the drop in brightness of stars as planets orbit in front of them. So you might have something like this, and you have these random points, you do a best fit to that, and this is how one particular Kepler 90I is able to measure that. So using these planetary systems with a number of stars that have been measured, they found 2,066 systems. This is in December 2017, so it's not too old, just a few months ago, this compilation. And this is with 2 planets, 386 systems, 3 planets, 129 systems. Now, remember what that means. If we have, for instance, our Earth goes around once a year, and we have Saturn that goes around once every 29 years, or Neptune that goes around once every 164 years, in order for us to see that there are 2 planets going across our sun, okay, Earth does it once a year, but how often is that going to be coordinated in any given direction with Neptune, which only goes in front of the sun in your direction once every 165 years? So to have our Earth and Neptune, not very likely. Now, it's more likely if we have something down in Mercury which has 88 days. Well, even so, to have something in line with us, we have to be looking at that particular day, 1 out of 88, and we might have that. So it's those difficulties that give rise to the fact that you have so many singular planet stars and many fewer. And to find something like this with 8 planets around it is kind of unusual. But of course, there's another thing that comes into it that I'll get to in just a minute. But this is just another way of laying out the planets that we've observed around other stars. Okay, let's look at this at first. This is our sun, and this is our solar system, and here is the habitable zone, and Earth is inside, Venus is a little bit on the inside, Mars is in a better position than we are, and this is one that they've been looking at, and here's the habitable zone for this, and notice all these planets are very close to one another, which means they're going around pretty much the same thing, and they're going fairly fast, so you have more chance of finding several of those planets in front of the sun to be able to measure them at any given time. This is TESS, which is Transiting Exit Planet Survey, which is being set up again. It's going to look at the whole sky, and it's going to survey, a 2-year all-sky survey, 26 observation sections, 13 per year. So it's going to do the northern hemisphere for a year and then southern hemisphere for a year. Another thing that's kind of interesting to consider is the fact that in a lot of this clumping of the material, not all of that stuff ended up being around a sun. There's a lot of that stuff just floating through the universe, through our galaxy. It's a big galaxy, so it's not unusual to say that, yeah, some of those clumps didn't get tied into a star. They just are loose and floating around. And we know that there's an awful lot of asteroids, meteors, all that kind of stuff. Well, is there a possibility that that might have life also? Well, come on. But on the other hand, if you think about deep sea vents, now there's 2 different kinds of deep sea vents. One deep sea vent is the kind that really requires chemicals that were generated from the sun and so on. But there's another type of deep sea vent that had no reason. There's enough heat coming from the core, there's enough chemicals in the sea floor and the ocean that it could invent certain limited kinds of life. So it's possible that these things are just floating throughout the universe, our galaxy, without any sun, could also potentially have some life. So we don't know, but it's a possibility. This is an indication of how many of those we can estimate that, because if we have a telescope here, and we have a star over here, and we have a planet, this one happens to also have a moon, and as it goes in front, you have the bending of space that takes this light and bends it around so that we would see a variation and a blip in the way the light from this sun gets to us, and we end up with this kind of a blurb. So we get a little bit of a magnification, And that sort of has to do with the way Einstein theory was proved back in the early part of the century. So planets drifting between stars throughout the galaxy, we can kind of get an estimate of those. It's another possibility for where life could exist. They have no sunlight, but could also form life. Think deep ocean vents where life abounds but never has sunlight. That's another book, Exoplanets, and you can look all this stuff up reference-wise. Here's a Webb telescope, sensitive to infrared. Hopefully it will see planet atmospheres, which would be another really exciting thing. This is going to be up, it's going to be beyond our Earth-Moon situation, further out than the Moon. It's only going to survive for about 10 years, I think. It was going to be put up on a certain schedule, but apparently when they tried to experiment with this to unfold this, because it's all compacted down, and they get it up there and they unfold it, some of these very thin foil things that shield it from the heat of the sun as it's looking out into the colder universe, some of those tore. So they wanted to make sure they could get it right, because there's no repairing it once it's up there. So it may be another few months, few years, I don't know, until they're able to get that repaired and reliable enough system that they're able to carry it out and do it. Okay, so it's really complicated. We found out a lot of information about black holes. We found a lot of information about dark matter. We found a lot of information about the Big Bang, multiple universes possible, neutron stars, gravitational waves, space warps, all kinds of really neat stuff. We still don't really know what's going on, but we're making progress. We're making progress. And there's a lot more questions than there are answers. So that's sort of where I'm at, and if we want to talk about it, that would be great.
Big question today, and it's more philosophical than it is scientific. So let's say that 20 years from now we discover what causes the Big Bang. But then we're going to need to know what caused the thing that caused the Big Bang. So my question is, will science ever be able to uncover the beginning of everything, or will it always be an unanswerable question?
That's an unanswerable question. The thing is, we don't know what we don't know because we don't know. So yeah, it's interesting. I think we're always going to be making progress. We're going to get a lot further, but so far we're really far away from understanding a lot of the details and the basics of all that kind of stuff. Maybe we don't have the mathematics. Maybe we don't have the capability of doing that. You've heard about string theory and all this other kind of stuff. Well, those are attempts to make things fit into it, but maybe we're still not going to be able to do it. I don't know.
Thank you.
Yeah.
You mentioned that half the stars out there are double stars.
Roughly.
Given the gravitational forces involved in a system like that, what are the implications for the formation and sustainability of planets?
Well, I don't know. Maybe they have found a planet around one of these double stars. I think they might have. They have. But it's a much trickier thing to have three bodies going around without smashing in and so on. But yeah, I mean, the stars go around each other in orbit just like the Earth and the Sun. So that works. But in terms of other planets, that's pretty unlikely. It seems to happen, but it's unlikely. Yeah.
Hi. I have two quick questions. First of all, when you said that half of the stars in the universe have companion stars,
Right.
do you know why that is?
Just randomness. Just, some stars have 3 planets, some have 18, some have, it's just a random kind of thing. Whenever things are clumping, whenever you pour water into a glass, why does this stuff splash out on this side, or how much of it? I mean, it's just kind of random sort of thing as far as I'm aware.
Okay. And then secondly, you said 4.9% of the universe is matter. Does that include the planets and
Oh yeah, that includes all of
stars?
us. Everything that you can see, you can touch and feel and so on, because we don't know what dark matter is, but it's all around us. It's just like, you don't know the neutrinos are here, but they're everywhere. There are more neutrinos in this room than there are light photons.
Is
And
that
they're-
considered matter? I mean,
which
everything that's
concern-
when you say matter, I mean,
Well, dark matter, it has a gravitational attraction, Okay?
But is that separate from the 4.9%?
Oh, yeah, yeah.
9%
It's
that-
4.9% of stuff like you
The
and me.
things that we can-
And then 26% or whatever dark matter, which has gravitational effects on us. And then dark energy, which is what's causing the universe to expand more quickly away. So we see all this stuff. It's got to work. It's got to be there for our formulas to work, to project out what it is that we actually see. But we have no idea how to touch it, feel it, and more about it.
Right.
Okay?
It's just an interesting thing to think about.
Yeah.
Thank you.
Okay.
Yes. And I would like to point out just one more thing, perhaps you may amplify it later, namely the effect of the so-called physical constants. We know that if the physical constant were very slightly different, maybe to the level of 10 to the power minus 15, then the nuclear reactions and the fine structure constants, etc., will be different.
Sure.
Then the reactions will take place in a very different way. Therefore, the possibility of life and habitable zone, etc., will be quite different. And maybe, well, we know that both from the past, for example, during the Big Bang, when the elements are synthesized, helium and other elements, they will also change. So from this we know that therefore the constants in our universe has not changed by more than this amount. But there may be other places, universes, where it may be different. Then you can have a very different type of life, maybe, different habitable zones, or maybe different exotic lives and so on. So that is another factor which can have a big impact on life, habitability, habitable zones, and so on.
Yeah. Basically, you're saying there's a lot. If we change some of the constants, and there's no reason why those constants couldn't be changed in some other universe, a whole different set of things set up, and there may be life there in terms of being able to reproduce itself and grow and do things and be effective in changing its own environment like we do here, but it might be totally different than we are. So, yeah, good point.
Right here?
Yes.
I haven't been following it, but how many LIGO events have there been, do you know roughly?
How many what?
Of the gravitational waves, how many events have they detected?
I think there's about 5 at this point.
Okay, I thought it was just a very few.
Yeah, it's just a very small number, and actually they've taken down now LIGO to make it even more effective for doing things. The neat thing was about a month before they took it down is when they found this neutron star annihilation, but that was particularly interesting also because just before that happened, Italy had put up their their gravitational wave detector. So now you had Hanford, Louisiana, and Italy. So that lets you point much more directly to where it is in the sky. And they were able to turn a lot of telescopes very quickly to that and see a quick flash of light. And since the gravitational waves and the light came at the same time, they know now that gravitational waves travel at the same speed of light within, I don't know, a trillionth of a gazillionth of a second or something. I mean, it's really very well tied down now. So that was one neat thing about having these other things. People were able to go back to old records and look to see whether there was a flash of light there and so on. So it's really, really great.
So they can see three-dimensionally?
Yeah, right. Oh, no, it's three-dimensional, yeah.
On the black holes, it wasn't relatively recently that we figured out the mass of the one that's the center of the Milky Way here, right. But they've also been finding other black holes. Has this contributed significantly so we could figure out what proportion of matter is black holes?
I think what we observe is a small fraction of anything related to that. So it really comes with, we have formulas that explain the overall structure of the universe where they do that modeling and so on. And there are certain constants you have to put in there to make things fit. So it's really from that kind of a thing. So we look at how fast things are expanding, and we know that from the observations like I indicated, and a whole bunch of things like that. So it's not particularly the black hole observations that tell us how much black matter there is. As a matter of fact, that provides some more conundrums because we can't figure out how the hell do you get a black hole that's, 50 times the size of the sun. We don't know of any mechanism for that to happen. So that's yet another thing to think about.
Yeah, the science fiction author Douglas Adams wrote a book called The Hitchhiker's Guide to the Galaxy. In that book, he proposed that a towel is the most useful item in the universe. Could you
A
comment
towel.
on that? Yeah, a towel.
Well, good for him.
Much simpler second question this time. Given our current political climate, I doubt that the best scientists on this topic are working in this country. What country do you think is doing the most interesting research and most supportive of this type of research?
I think for one thing, it depends a little bit about what kind of research you're talking about, and that's always a changing thing. We were doing a lot of really neat stuff here in this country, and then that got downsized so that the big collider that they have over in Europe, that was originally started in Texas, and then they decided to unfund that. So it moved over there. Also, this idea of combining masses together to convert mass into energy, they used to have some pretty big stuff here. They've decided to put their $50 billion and more into a situation like that in Europe. China is doing an awful lot into space and going to go to the moon pretty soon. And so it moves around a little bit. Some of these other countries are well ahead of us in terms of nuclear power and what they're doing with that. So it's a little bit spotty here and there. But, one of the things that comes out is that if you take a look at the recent science high school people, something like 82% of those have foreign names, okay? They are not old white Americans like me. So I think that indicates that there are an awful lot of people that are coming to this country for jobs and for high-tech stuff, because Silicon Valley and some of those others are still some of the main things, but that's migrating to other places now. So it's hard to say who's going to win that race. I don't think it's going to be anybody in Africa. I don't think it's going to be anybody in Mongolia, but China, Europe, certainly Japan might still be in that in some areas, because they're doing some of the gravitational work also. It's up for grabs.
Oh, mine has something to do, my question has something to do with his also, and it's about the funding. You know, NSF is cutting their funding, NASA, Department of Defense has plenty for this kind of thing, but what do you see the future funding? Are corporations going to take this over, or other governments?
I think what we really need is something to scare the living bejesus out of us. Whenever I was in the military, I already had my bachelor's degree, and I'd gone through boot, I was working in a research thing in a hospital, and then Russia's put up Sputnik. And they said, man, get all these critical skills guys, educated people, science, back to their civilian jobs. I got out, I went to graduate school, I had probably 25 people in my graduate school class, every one of them got funding. We're just moving away from that, and we're, as you saw, I mean, I was surprised. Here's a medical doctor who's saying, what are we wasting all that money for? But that's just the way it is. So if you have your kids raised, send them, let them learn to speak Chinese.
I was wondering what the working definition of black holes is.
Black holes. Black holes are something where it has so much gravity, has warped space so much, that light goes in. Anything that goes into it is not able to come back out. So if light goes into it, it stays there. Now I have to put a little asterisk on that, because there's a not quite true kind of thing. But for the most part, it's black because everything that hits it goes inside and stays there. The one exception is that there's a real weird thing in quantum mechanics where things can just annihilate out of perfect vacuum, and it's there, okay? Well, if that happens right at the surface of a black hole, it can do this, and one of them falls inside, but the other one goes in the other direction. So that's radiation from a black hole. Very small amount, though. And we're trying to find, can we observe that or not? Well, we'll see. But
I noticed that the Italian experiment that you put up there had estimated a size for the particle of dark matter.
right.
If the Italian experiment is wrong, are there any estimates of how big the chunks of dark matter have to be?
I'm not aware of a specific size, but there's an awful lot more talk now about not just big black holes, but small dark matter particles, or whatever you want to call them. And perhaps they are what really comes together to start forming some of these black holes way back in the original blow-up of the universe. Okay, so they might have started clumping together after a couple of 100 million years. And it could be there's an awful lot of those just going around throughout the atmosphere, throughout the universe everywhere, and maybe some of them clump together, because to make these big black holes, you don't have an awful lot of black holes floating around, relatively speaking, for them to come together and form that. So maybe it's these smaller pieces of dark matter gravitationally attracted to one another that come together and produce those, just like hydrogen and stuff clumps together to make our sun and so on. So that's one of the possibilities. Yeah.
My question is about intellectual property. You mentioned Italy will not share their information. Who owns information? Is it the scientists at Bell Labs? Is it Bell Labs? Is it the government funding that Bell Lab gets? Where is the where's the leverage of the person who comes up with the idea?
Specifically for the Italians, I don't really know who owns that, but I would imagine it's the people that fund it, say whether they're going to extend their funding again or not. But if you're a well-known scientist and, hey, you got something special here, you know, why not? Something like Bell Labs, well, there's two things they do. One is they patent stuff that might be really useful, but they're also publishing all the time. And they're reading other people's papers and stuff. And usually the stuff that's published is not so much patentable, maybe applying that to make something that's going to be worthwhile. So your telephone and all that other kind of stuff. But on the other hand, people started eating our lunch, which is why we have the vast array of stuff we have, instead of good old Ma Bell with one black telephone with a cord attached to it and all that kind of stuff. So, yeah. Yeah.
About telescopes that find exoplanets by measuring dips of light, that works well for stars we're viewing from our planet at their equator. Is there technology available to look at stars where we'd be facing their poles, maybe block out the light and maybe find planets that are circling around like that?
No, there's another technique that can be used also to find planets, but also very much the same, maybe a little bit broader in its access, not just the diameter of the sun, but, you know, whenever the sun is here and the earth is here and they're going around each other, the sun doesn't exactly stay here. It's like square dancing. You know, if you're a big guy and a small woman like my wife, we go around like this. We go around a center of gravity. So that makes the sun wobble a little bit, and that wobble can be measured if you're very careful about measuring the spectra because of the Doppler shift. So you can get a little bit of a feedback from that. And as a matter of fact, that lets you measure maybe, I've seen as many as 7 or 8 planets that have been deduced because of the variations in the wobble that the sun has had. So
I've noticed, like, for every scientist, there is talking about, say, this huge array of unimaginable things like, you know, black holes and neutron stars and gravitational waves and on and on and on. For every scientist, you know, there's hundreds of people who know very little about science that are talking about these things too, and you know, working them into, you know, some sort of fantasy, and then most people have trouble distinguishing between the two, and science loses credibility for these things that you can't see, feel, or touch. I don't know how to say it, but there's a strange kind of skepticism that works against science. Does that make sense when I'm saying?
Oh, absolutely true, and you're absolutely right. And one of the problems, I mean, I think it's great that we do get some stuff out there. Certainly a lot of science magazines provide all this kind of stuff. But I was talking to somebody, I don't know if I mentioned it, the creationists are alive and well. I mean, people say, oh, they don't really believe 6 Yeah, they do. I used to teach classes over at Willamette View for several years, and one of the guys that came to my classes was a creationist. And he invited me to go with him to a meeting, so I went. And I didn't ever go to their religious meetings, but I went to a lot of their other discussions and so on. And I did that for 3-4 years. I really got into it. I read their literature. I watched their movies. They really do believe 6,000 years old Earth is it. And I can talk on and on and on because it's one of my favorite topics. I'm going to give a talk about that to another organization in a couple of weeks. So if you want to talk, we can talk a lot more about that. Thank you for having me.